So what we're going to talk about now is Reynolds experiment, sometimes pronounced Reynolds experiment, kind of like Reynolds wrap, the same name, not not the same person, but the same name. So Osborne Reynolds uh, explained the strange shape that we were talking about in the previous video with the curves of the pressure drop experiment. In a apparatus similar to that of figure 1, in which there was a tank of liquid, there was a flow regulating valve, there were two pressure gauges, liquid was flowing into a bucket. Reynolds arranged to introduce a liquid dye into the flowing stream at various points. He found that in the low flow rate region, in which negative dp dx is proportional to the flow rate, the dye he introduced formed a smooth, thin, straight streak down the pipe. There was no mixing perpendicular to the axis of the pipe. This type of flow, in which all the motion is in the axial direction, is now called laminar flow. The fluid appears to move in thin shells or layers, or laminae. And so you see here, this bottom portion of the diagram, it's laminar. Everything is straight, thin, smooth. There's no sense of turbulence. So this is a somewhat usually desired type of flow in any type of fluid mechanics, any type of transporting fluid. Usually this is more of the preferred method. They like laminar flow, much smoother type of flow. Reynolds also found that in the high flow rate region, where negative dp dx is proportional to the volumetric rate to the 1.8 to 2.0 power, no matter where he introduced the dye, it rapidly dispersed throughout the entire pipe. A rapid chaotic motion in all directions of the pipe was superimposed on the overall axial motion and caused the rapid crosswise mixing of the dye. This type of flow is now called turbulent flow. Turbulent flow, you see here in the upper portion of this diagram, is just as what I said. It's chaotic. It's not straight. It's not smooth. It's very, very rapid, chaotic motion, going all over the place. There's no organized flow or anything. Usually not the preferred type of flow, but it can be. The two types of curve, linear and approximately parabolic, in the figure in the previous video, thus were shown to represent two radically different kinds of flow. The distinction is very important, as we will see. Students should observe both types in the world about them. Perhaps the easiest example is to see smoke from a cigarette rising in a still room. I'll draw a cigarette, or I'll try to draw a cigarette. And you see a cigarette here. Yes, this is a cigarette. I know this is a horrible cigarette. This is a cigarette though. And you see smoke. And right now it's more of a laminar flow. And the smoke rises in a smooth laminar flow for about a foot, and then the flow converts to turbulent flow. It starts I don't know what's going on. I'm having trouble operating. Here we go. It starts going turbulent. It's not in that laminar. It's sort of goofy. Point here is that the smoke begins to be laminar flow and then transitions to turbulent flow. This case, although easy to demonstrate in the laboratory or the living room, is much harder to analyze mathematically than Reynolds' pipe flow experiment, so we will return to the latter. Reynolds showed further that the region of unreproducible results between the regions of laminar and of turbulent flow is the region of transition from the one type of flow to the other, called the transition region. So in the middle of this can be called the transition region. And the reason for the poor reproducibility here is the laminar flow can exist in conditions in which it is not the stable flow form, but it fails to switch to turbulent flow unless some outside disturbance, such as microscopic roughness on the pipe wall, or very small vibrations in the equipment triggers the transition. Thus, in the transition region, the flow can be laminar or turbulent, and the pressure drop or flow rate can suddenly change by a factor of 2. Under some circumstances, the flow can alternate back and forth between being laminar and turbulent, causing the pressure drop to oscillate between a higher and a lower value, or for a constant pressure drop, as in figure 6.1. The velocity can oscillate between a higher and lower value. Besides clarifying the strange shape of figure 6.2 with the chart with the curve of the pressure drop, Reynolds made the most celebrated application of dimensional analysis in the history of fluid mechanics. He showed that for smooth circular pipes, for all Newtonian fluids, and for all pipe diameters, the transition from laminar to turbulent flow occurs when the dimensionless group d, the diameter, multiplied by v, the volume, multiplied by rho, the density, divided by mu, the viscosity, has a value of about 2,000. Here, d is the pipe diameter, v is, I just misspoke, it's not the volume, it's v is the average fluid velocity in the pipe, rho is the fluid density, and mu is the fluid viscosity. This dimensionless group is now called the Reynolds number. So here's Reynolds number. Reynolds number, denoted by this fancy R, is equal to the diameter multiplied by the fluid velocity multiplied by the fluid density divided by the viscosity is equal to, that's a d, diameter multiplied by the velocity divided by the kinematic viscosity, which is fluid density divided by viscosity. That's kinematic viscosity. Sorry about that. That's kinematic viscosity, and it's equal to negative 4q, or positive 4q, over pi diameter times kinematic viscosity. Q being the volumetric flow rate. So it's important to note that the behavior of, let's say, a die streak in laminar flow, flow in, flow out, it's straight, it's like this, transition oscillates between laminar and turbulent, so in between turbulent and laminar, it's oscillating between laminar and turbulent. Common sense. And obviously there's turbulent. We see that the pressure drop proportional Reynolds number. We have Q, which is the volumetric flow rate, usually proportional to Q to the 1 power when it's a laminar, and then turbulent, it's proportional to Q to the 1.8 to 2.0. 1.8 if it's a very smooth pipe, 2.0 for a very rough pipe. This is what I've already said, but what's new that I haven't told you yet is that Reynolds number is less than 200 for laminar flow. And between laminar and turbulent, it's between approximately 2,000 to 4,000. It's difficult to measure when it's in between laminar and turbulent. And for turbulent flow, Reynolds number is greater than 4,000. So laminar flow, less than 2,000, and between 2,000 and 4,000, and for turbulent, greater than 4,000. I will continue to discuss laminar flow in the next video. So see you in the next video.